All right. So, hello and welcome to this next lecture in the ongoing series of lectures in digital prepress. So, let us start this lecture. I think we left off the last lecture by where I showed you how actually digital halftoning is done. I mean, some of the algorithms I had shown you. One mainly thresholding algorithms, and that is for the aim techniques and error diffusion technique for FM screening. I will try to show you the effect of the image, effect on the image that these two types of modulations, one is amplitude modulation and the other is frequency modulation, actually has. Now, another thing I would like to point out before I go ahead with this lecture today, that is, I think I have a picture somewhere. Let me just check that. Yes, I wanted to show this one. You see, the I mean, at the end of this, or maybe next lecture, I will be doing a very detailed comparison between AM and FM screening. But just to give you a brief overview of what it is, see, normal. I mean, for any given printed matter, normally you would see that FM is appearing to be more smoother to the eyes. Smoother in the sense that more continuous to the eyes, human eyes. Because in case of AM, there are certain artifacts which are inherent to it, like the rosette effect that you can see on the screen. So, as a result of all that, it is sometimes, or not sometimes, but normally when you see uh, the same image, one is screened with AM and the other is screened with FM, you would notice that the one image which is screened with FM appears to be more continuous in nature. Now, I am not going into all this. So the again, I am just repeating again one thing, that what is the overarching message, or what is the overall fundamental difference between AM and FM. That is, in case of AM, you only decide what is the size of the dot. That is a determining factor to create shadow, I mean tone aberration essentially, right? But in case of FM, all you have to determine is the number, first of all, and of course, more than the number, I would say the distance between the dots. So if you reduce the distance between multiple dots, then that would represent a shadow area. If you uh, extend the distance between two dots, then, or multiple dots, then that would represent a highlight area. So this is sometimes referred to as FM is sometimes referred to as stochastic. It's not really random, it's pseudo random. So I'm not going into details of all that, why that is and what are the different types. I just showed you one very basic type of FM screening. So that should do, I think, that should do, that should give you a brief idea about what really it is. And now let us start our discussion for today. See, again, I would like to start with the same concept of resolution, because this is very much important. Okay, uh, I think in today's lecture we will be covering one of the most, if you remember in the earlier lectures, I had covered something which was known as your and I had not covered, actually, I had given you a brief overview on uh, the elements of digital prepress, where I had used one term, that is transfer function, optical transfer function. So here we will be studying a little bit about that and how all that comes together, etc. But before that, let us again uh, consider this. Okay, so now take a look. We will start. So many pictures are there, not to worry, I will explain each one of them. I will try to explain each one of them. So yeah, starting with your screen frequency. Okay, now your screen frequency is very much simple, that is how many number of lines are there in your screen, right? So that ultimately entails what? Lines means what? Lines are made of, in case of your AM screening, lines are made out of your halftone cells only, or halftone dots only. So how many dots are there in, or how many lines of dots are there in a linear inch, right? And so in the, that is what it is, right? So lower the resolution, the image will not look very continuous. Greater the resolution, the image will look more continuous and more detail will be obtained in those higher resolution screens. In the this particular image, as you can see that here, the frequency, uh, if you hear the if you divide the screen frequency in half, the half tone will become 4 times as big. If you remember, I had shown you exactly this thing. If you remember our earlier lecture where I had considered a screen cell of 14 by 14 pixels, I told you for a CTP which is considering a of a certain resolution, which is considering a screen cell of size 14 by 14, there you will get a one dot. Assume, okay. Now, if you have a higher resolution CTP which is capable of driving higher resolution output, then that same 14 by 14 screen cell is capable of reproducing 4 dots. So normally this will have, if you take, just take a look at that thing, that lecture. So if this was your 14 by 14 grid, that is the screen cell, if this was your screen cell with a lower resolution CTP low, right? Then this entire thing would reproduce one dot. But at a higher resolution CTP-H, the this 14 by 14 would be divided into like this. The same area would be creating 4 different dots because the resolution is high. The same, 7 by 7, 7 by 7, here the entire thing will be represented by 7 by 7, 4 blocks of 7 by 7 screen cells. So here we used only a single screen cell, but with a higher resolution CTP we are capable of displaying or representing the same area of the digital image using 4 dots. That means using 4 screen cells, right? That same area, that same 14 by 14 pixel screen cell, now I have divided into 4 blocks of 7 by 7 pixel 7 by 7 grids. So that means what? The number has essentially quadrupled. The number of dots that can be reproduced has quadrupled. So the resolution is increased. So in the same, why am I saying resolution is increased? Because in the same area is represented not by one but by 4 dots. Naturally, the amount of detail will be greater in this area, is it not? So that is what resolution is all about. Okay, now another very important thing, this particular concept here, the resolution versus screen frequency. I've already explained that earlier also, but okay. See, now acha, I think you are not able to see this, so I'll just write it down over here. This is actually written as exposure dot. This is what is written in this area, which you can't see because of my face actually. Okay, so now see, three concepts. Again I'm repeating this. See, although I have already told you this in the previous lecture itself, but again I'm repeating this because this might sometimes lead to some confusion. So listen to this very carefully. We are having a digital image. Digital image is made out of what? Pixels, right? So maybe your digital image is made out of 200 by 100 pixels. Hmm. Now we need to do what? We need to represent those pixels as dots in a plate to be printed. That is what? We cannot print pixels. Our printing system does not work like that, isn't it? So what we start with is an image whose resolution is measured in ppi, pixels per inch, right? Now this is that block of pixel which is considered for reproducing a single halftone dot. Listen to this very carefully. Your image is made out of 200 by 100 pixels. Now you need to represent the entire image with you need to break down the entire image into some blocks of pixels or grid of pixels, and each of those grid is representing one dot, or for, you can see in this way also, or for each grid one dot is being created. Okay, understood? This block, this chunk or this grid of pixel is known as what? It is known as screen cell. Here it is written halftone cell. So I will just uh, okay, so hold on. Yeah, so I will just cross this one out and I will just write, because we are using the same term from before, we will write screen cell, so that half tone cell they can call, no issues, you can also call, but since we have used the term screen cell, I will use the term screen cell only. So that now, so this concept of screen cell is clear now. What is a screen cell? So your screen cell is your, what should I say, the minimum size of the, or minimum conglomeration of some pixels into which your entire digital image is broken down, and one screen cell corresponds to one halftone dot. Now acha, let me just clean this up, okay. Fine, I will just show here also, here only. Acha, see, in this is, let us say this is representing the same area or same image. Let us say this screen cell is also representing same area, this screen cells are also representing same area. Now the question is, here we see the size of the screen cell is large. Try to wrap your head around this concept, okay. Screen cell, I told this concept in the earlier lecture also, so if you had some confusion there, try to clear that up, because I told you, no, if the CTP's resolution is high, then the screen cell will become smaller and smaller. More the resolution of this your CTP, smaller will, so that might get confusing a little bit. Now try to listen to this carefully, what I'm telling you. Okay, see, for this screen cell I am saying that this entire thing, this entire you know part of the image, so this is a part of a bigger image, right? This is a part of the bigger image like this, okay. So this image has been broken down into some screen cells like this, maybe four screen cells like this, four screen cells like this, okay, or of size 14 by 14 pixels. Each of the screen cell size is 14 by 14 pixels, let us assume, okay. So what is happening, this is at a certain resolution, you are getting a screen cell like this. But for a different CTP, for a different imaging system, you are saying that the same image can be, instead of uh, uh, 4, instead of 4 you are getting 16 screen cells, of each of the screen cell size is 7 by 7 pixels. Why? Because you see, the same screen cell has been broken down here into smaller screen cells of 7 by 7 each size, right? So instead of getting a single screen cell here, you are getting 4 screen cell. That means the size of the screen cell has shrunken, has reduced. That means the amount of detail that you can show will increase. Why am I saying amount of detail will increase? The same area here, the entire picture is represented by, imagine the entire picture here is represented by 4 dots only, but here we are using a different CTP which is capable of driving at higher resolution. That same image can be reproduced with the help of 16 dots. So which is capable, which CTP is capable of creating more dots in the plate? Of course, this higher resolution CTP. So more dots in the plate means what? Greater resolution, greater image quality, right? So that is what the concept of screen cell is. Okay. Now, next comes the concept of halftone dot. This I think you know by now, that one screen cell corresponds to one halftone dot. This is analogous. So okay, another issue is there, that is your this thing, that what is the or let me put it in this way, that one screen cell will be responsible for producing one halftone dot. This is strictly, I am talking strictly about aim screening. I am strictly talking about aim screening. Keep this in mind. When you are talking about LPIs, PPA, these are all aim screening things. Okay, fine, understood? Okay. Now, when I am talking about a screen cell, I am talking, that means screen cell means a single halftone dot. So here, one screen cell, see, this is one screen cell, right? This is producing this size of a dot. But here, the same area has been divided into 4 screen cells. So don't say later on that, okay sir, this is one screen cell, but here there are, this number of dot is 4, so one screen cell is producing 4 dots. No, please clarify this part very carefully, very nicely. The screen cell itself has reduced into smaller components. Screen cell itself has reduced into smaller components. There are 4 screen cells. See, there was here only one screen cell. Now here, because we are working with a higher resolution CTP, there are four screen cells represented in the same area. That means one screen cell here also corresponds to a single dot. That means I'm writing it down. One screen cell corresponds to one halftone dot. Keep this in mind. Very important thing. Okay, understood this part. Now, next part is your, this is what is known as the exposure dot. Yes, this is very important. Now we will slowly and steadily, why I am saying that this CTP is higher resolution and this CTP is lower resolution. Now we will come to that concept. Actually, if you did not understand the earlier lecture, then actually the you know the what chronology of this part is like this only. You have to first get into AM screening and FM screening, then you come to this part. So after seeing this lecture, maybe some of the concepts which were you could not understand in the earlier lecture, those concepts will now become clear. Now listen. So two things is clear: screen cell and half tone dot. Huh? This is clear. Okay. Now, so one screen cell corresponds to one half tone dot. And also I have given another thumb rule to you. What is that? That your higher the resolution of the CTP, greater will be the number of screen cell, but the screen cell itself, the size of the screen cell itself, screen cell means block of those pixels, that will come down, that will shrink, reduce in size. These things you have understood till now. Okay. If you have not understood till now, just go back, listen again, and then uh, start again from this point. Okay. This is quite important. Now, last this part is talking. We will be talking about the exposure dot. See, CTP basically is a machine which CTP stands for computer to play. That everybody knows. That is not nothing new. So what CTP does is, if you before talking about the CTP, what I like to talk about is I think in the previous semester when I talked about Prepress Repro, just if you think hard enough about that, in the proofing this lecture, I told you how the inkjet drops are being sprayed onto the paper. You are you have a inkjet printer in your home, a desktop printer, a normal desktop printer. How those drops are created? How does it know where to put the dot? CTP also is the same way. What happens is, let me just show you with a piece of paper. I think I have a piece of paper here somewhere. Okay, so yeah, so I don't know if you can see this. Let me just check. So this is a piece of paper. Okay, this is a piece of paper. Now consider that you are this paper is representing your plate which you are inserting into the CTP machine. So what CTP does is, it has got your image size and it is also your plate size. What it will do is, I don't know if you can see this, maybe let me just adjust the light. Yeah, now I think now you are able to see. So what it will do actually is, it will break down the entire plate into this grids, right? This grid type of a pattern. Hope you are able to see this grid type of a pattern like this. So that grid is similar to some pixels, right? Now what it will do is, once this grid type of pattern is obtained, then it will decide which small box within that grid has to be burnt. CTP does only a simple thing, that is, it burns certain area. That means it exposes the plate. If it's a this if you have inserted the plate, and if some area, it will expose with the help of a laser light, and the exposed area will get the coating in the exposed layer will get hardened. If you wash it, unexposed areas will wash off, and the exposed area will become the image area, right? So this is a basic concept, same to our normal this thing only. But here lasers and all these things are used. So I think in surface preparation techniques and all, you will learn a whole lot detail about how CTP actually functions. That is different. Now, so this is the principle of how CTP operates. This is a very basic principle. Now the question is, how does the CTP decide how many grids to prepare and how many lines are there in the how many lines or how many boxes are there? So that is where the CTP's resolution comes in, and you will see that everything is interrelated. See, this is see hopefully you are able to see the area where I have written exposure dot. This entire thing is a screen cell. Okay, let me just draw it. This entire chunk of cell or pixel is the the screen cell, right? This entire block of black area, that is your halftone dot, is it not? Now, what is the individual size of this, or what is the individual box? This individual box is known as the exposure dot. That means the CTP is burning each grid at a time. Not at a time, and it's not like that CTP is burning, the lasers are burning one cell at one time and then this cell. No, not like that. It will burn all the cells together only. But I'm saying, what I'm trying to say is that CTP considers this to be the basis or the unit of what it is going to expose with the help of its own lasers, or what is it is going to expose basically or burn. So this is the unit, right? This is the unit. Now multiple such units, multiple such boxes, when they are bound together, then this type of a halftone dot appears on the plate after development, right? Is it clear? Hopefully it is clear. Again I am saying the CTP, so the entire outer thing is the screen cell, the bigger black thing is the halftone dot, but the individual boxes which makes up the halftone dot, that individual boxes are burnt or exposed by the lasers of the CTP. That is, the individual boxes or individual areas are the fundamental units of imaging for the CTP. Right? Now the question comes, here screen cell is measured with what? What is the resolution of the screen cell? Screen cell's resolution is PPI, is it not? PPI. Halftone dot's resolution is what? LPI. Then what is the resolution of exposure dot? What is the resolution of what is the unit of this exposure dot? How to measure how many exposure dots? It is DPI. I had intentionally not talked about DPI for quite a long time now, but now from this class onwards I will also be talking about your DPI. Now I am asking you a question, that what is the kind of how do you say, what is the kind of relationship between your screen cell pixels, or PPI you can say, and DPI? Or then okay, fine, I will ask that, I will go to that part a little bit later, but now let us address one important thing, that is, we have established the three different terminology, that is screen cell, halftone dot, and exposure dot. Exposure dot is the minimum area which your CTP can expose with the help of its laser beams, right? Now tell me, I have a CTP, same question again like previous one. I have a CTP which is having a resolution of 1200 dpi, and another CTP which has a resolution of 12,000 dpi. So what does it mean? What does this term mean? That's it. And when you go to the industry, you will when you are working in offset industry, you will see if your company has CTPs, then you will find out there is a resolution of the CTP and all. Okay. Now, what does this term mean? In halftone screen, I know what it means. Halftone screen, if I say this halftone screen is 175 LPI, I know that. In 1 linear inch, rows of or columns of those halftone dots, that number is 175. 175 lines of dots, right? in 1 linear inch. That I understand. That is okay, fine. But for what does it mean for the CTP if I say it is CTP of 1200 or 12,000 dpi? Can you answer this question with the information that I have just told you about exposure dots? I hope you will be able to answer. Just pause the video here for a minute, think about it, and answer the question. This means that there are enough number of lasers in the first CTP to create 1200 1200 exposure dots in 1 inch of space. Okay, that means, so I think, okay, let me just draw this out. So this means what? That for, let us say that this is the first CTP. Okay, this is, let us say both the CTPs are working with the same size of plate, then our comparison will be much more better. This CTP is having a resolution of 1200 dpi, this CTP is having a resolution of 12,000 dpi. Okay, this by the way, 12,000 dpi CTP is very rare and very, I mean, not rare, but it's very costly actually. I mean, very few people, very few I mean, companies use this high resolution CTP actually. I think Luxor or some companies, they are making very high resolution CTP. Okay, fine. So maybe this is a certain size plate, maybe this is 1922. The plate size remains the same. Okay, and let us say that I am magnifying for better understanding. Okay, let us say that this is 1 inch, this area is 1 inch. Okay, I mean, this length is actually 1 inch, this length, this is 1 inch. Of course, visually, if the entire thing is 22 inch, then this will not be 1 inch. Obviously, this is understandable, but just for explanation purpose, I am telling you. So this length is 1 inch. Okay, similarly here also this length is 1 inch. Now what is the CTP going to do? It will burn off certain areas. How it will burn? It will break the entire plate into those small boxes, right? Exposure units or exposure boxes, and then it will throw the laser light, and that particular box area will get exposed. Now there you will see that I think in surface preparation case will teach you about these various types of dots and their dot profiles in digital CTPs, and your this Gaussian curves, and this your GLVs, vibrating light bulbs, and all these new technologies that are there in CTP. So that is, I'm not going into those. I'm just going into the pre-press part. What you need to know, that I'm talking about. Okay. So as I was saying, that this is 1 inch of length. Now, for a 1200 dpi resolution CTP, what it will do? It is capable of creating, I mean, not creating really, it is capable of considering this length or dividing this length into 1200 such boxes. So this will go on like this up to 12, I mean, within this range, within this 1 inch, it will be creating 1200 such small boxes. And what will happen? It is capable of burning each of the box areas. That means it is capable of burning this individual boxes like this. But on the contrary, this 12,000 dpi CTP will divide up this entire same length, that is 1 inch length, into 12,000 such small boxes, and it is capable of burning each of the boxes separately. So naturally, tell me now, which CTP will give you the better output in terms of the fact that which will be able to produce more number of dots within the same space, where the screen cell size would be lower? Of course this one, right? Of course this one will be having lower screen size, screen cell size. That means higher resolution, greater number of dots in the same space. That means higher detail will be obtained, right? So this is somewhat similar. Don't you think this is somewhat similar to this concept as I told you earlier, that this is a CTP, let us say, is of 1200 dpi. So it is creating this much amount of the screen cell size is, let us say here, 14 by 14 as the same example I told you, 14 by 14 screen cell. So the 14 by 14 area of the screen cell, for each of that screen cell it is creating one dot. But here, since the number of the resolution is higher, that is why what is going to happen, the same area will be divided into not one screen cell but 4 screen cells, right? Therefore the number of dots will also increase. Now comes the question that what is that factor which determines the resolution of that CTP. Basically, CTP works, that basic principle is that there is a array of laser, and each of this is capable of throwing off laser light into your plate. Greater the number of physical lasers is there in this CTV machine, greater will be the resolution. So naturally, it will drive this number of lasers. How many number of lasers are there? That will determine what is the resolution of the CTP. Greater the number of laser hits, greater will be the resolution. So that is what it is. Okay. Hopefully this is clear. Now we come to the topic that there is a connection. There is a connection between these three concepts, that is your screen cell, your halftone dot, and your exposure dot. Or to put it in another way, there is a connection between your PPI, LPI, and DPI. So what is that connection? Now, as you see the last image, there is that a digital image should have a resolution in PPI that corresponds to double the screen frequency. Okay. When you go to print the page to a plate or on a printer, an output resolution DPI that is at least 10 times as large as the screen frequency LPI is required. Now, I will tell you why this is required. There's two things you came to know from here. That is, the relationship between PPI and LPI is, PPI and LPI is that PPI should be twice as much as LPI. So let us say you are using a halftone screen frequency of your 200 LPI. Okay. Now then what should be the minimum value of your or minimum pixel intensity in your image, in your digital image? It should be 200 PPI. Only then you can print it nicely using your 100 LPI screen. Similarly, for your this halftone screen, if your halftone screen is having a resolution of 100 LPI, then the output device should support or should have a minimum resolution of 1000 DPI. Okay, so this is basically the relationship. Now the concept comes that why. First, two things is the first relationship between PPI and LPI, and then relationship between DPI and LPI. I will talk about these two things separately. So first, consider the relationship between PPI and LPI. So this is basically known as something which is known as the half-toning factor. You remember how many factors were there during scanning? Two factors we considered. One was your this sampling factor, and the other was your scaling factor. When scaling factor, you consider the input frequency and the output frequency also for the devices and your image. But normally we consider only two factors, that is sampling factor and scaling factor, if you remember that. Here I am going to introduce another factor, that is half-toning factor. Okay, very simple thing. See, it's a common sense thing. See, this, try to look at this image very carefully. This is this square boxes. These square boxes, they are pixels. That means this is a digital image. Okay, and this this black areas, this is representing some halftone dots. Okay, this is representing some halftone dots. That means what? I am trying to draw a parallel between PPI and LPI. That how many PPIs should be there to support a certain LPI screen, or conversely also true that what should be the halftone screen if I want to print a certain digital image of a given resolution X PPI. Okay, so that is what I am trying to establish. What should be the relationship? What is written? The halftone screen shown here is angled at 0 degree, right? No angle, 0 degree. if the pixel resolution were calculated at twice the line screen resolution, that means PPI. I mean, pixel resolution is what? This is PPI is calculated at twice the line screen resolution is what? LPI. Then the RIP would use 4 pixels to calculate each half tone dot. This is clear or not? If this, see in this box here, this is your PPI, right? Here how many pixels are there? How many pixels are there? There are total, in this chunk of pixels, there are a total of 4 pixels, is it not? Now how many, if there are 4 pixels here, then how many for this 4 pixels, how many dot is being created? 1 dot. So if this relationship is followed, that is, if PPI becomes whatever the PPI is, then the PPI should be twice as large as the LPI. If this relationship is followed, then your RIP engine would, what is the function of RIP engine? Again I am saying I will talk about RIP engines in detail again in the end, but basic function again I am saying that it is figuring out these things. How many, what should be the size of the screen cell? What should be the size of a dot here in a specific area? Okay, how many dots should be there if you are using in a FM screening? So all these things, all these algorithms, like previously in previous lecture I showed that how AM screening is actually done, digital AM screening is actually done, how and if FM screening is done. Those mathematics, those algorithms are done by your RIP engine. So that is the main function of the RIP engine. Rasterizing, it is RIP's main, full form is only raster image processing. So it is essentially rasterizing your digital image into some dots. Okay, so fine. Now as I was saying that if you are following this relationship, that is PPI is twice the LPI, then for these 4 pixels, how many dot is being created? 1 dot. This is the dot, right? So this seems to be very simple. That is why in the previous slide also, this generalized, this thing was given actually. Okay, here you would see that same relationship is being maintained. See, very nicely it has been shown. If you draw this boundary, you will see that this is made out of 4 pixels. If you draw this boundary here also, you will see the boundary here also, the 4 pixels. That means here 2 pixels, 2 pixels together and 4 pixels in total were used for creation of one halftone dot. This is followed when you are following this relationship, that is PPI is equal to twice that of the LPI, right? So here if you consider the unit space, that or unit length, then how many dots are there? 2. For the same area, here there are 4 pixels. So that relationship has been followed, but this is not always true. We don't always use a PPI LPI relationship of 2. Sometimes it is required that some other values may be used. What is that case? See, in this first example, what was the screen angle? It is 0 degree, right? No screen angle is used. But here when we are trying to generate screen angles which is not 0 or 90 degree, then there would be a problem. Where, how? See, it is written that if you overlay the same pixel resolution of the of twice the line screen, there you will, here as you can see, here you will notice that there is no direct relationship. See, if you consider any 4 pixel for that matter, let us consider this 4 pixel, right? Here you consider 4 pixel, then just below it you consider 4 pixel. In the previous example, what did we see? For every 4 pixel there is a single halftone dot. For every 4 pixel there is a single halftone dot. For every 4 pixel halftone dot. Every 4 pixel. Now, but in this case, when the screen has been rotated by 45 degrees, see, screen has been rotated by 45 degree. Now, in this case, when the screen is rotated, then this relationship between, that is PPI is equal to twice LPI. This, if you follow, then there will be a problem. What is the problem? Now you have realized already. See, consider these boxes, 6 boxes that I have drawn. right? So here's what is okay, fine, this is a good test for you. In this particular case, in this particular scenario, uh, or better still, in this particular scenario, what is the size, if I ask you, what is the size of the screen cell here, screen cell used, what is that size? You let me know. Now, here in this case, you'll see that in the, as in the earlier case where we had not used any screen angle, it was four screen pixels corresponded to one half tone dot. But here, does it always ensure that four screens, I mean four pixels ensure one half tone dot? No. See here, the pixel is one half tone dot is here, but in this, a part of the half tone dot has come here and another part of half tone dot is come here. So this cannot be done because pixels or exposure dots in your CTP cannot be partially lit. It will either be fully lit or it will be switched off, or it will not be exposed in case of CTP. So no direct relationship can be found out between LPI and PPI if screen is rotated. Okay. Now, what is the uh, solution to it? Solution is very simple. That you use a half toning factor of 1.41, that is root 2. In such a case, if you consider that, then you would find out that each of the, for that relationship, that is if uh, that means here the Halftoning factor is what, 1.41, that means PPI is equal to 1.41 LPI, root 2 LPI. That means each of, for your one or unit PPI, there is 1.41 times LPI. Here you will notice these halftone dots that you are getting is almost similar or almost very much uniform in comparison to the previous scenario. The basic point here that I am trying to make is that what will be the number of uh, you know uh, pixels and what will be the corresponding number of dots, right? That is what the relationship is all about. Now the question here, or the point that I am trying to make here, see, if the number of pixels that becomes too less, too low, then your resolution will go down, you will not get that much amount of detail. But if the opposite thing happens, that means the number of pixel is quite high, that means this pixel density actually, or pixel per inch resolution, this goes very high, right? That does not always ensure that the quality of print is higher, because you have, why that does not happen, that I will come to the next step when I talk about relationship between LPI and DPI. But ultimately what happens, you will see that if you use a half-toning factor of 1.41 when you are rotating the screens for different screen angles, then the half-tone structure, overall structure, will become almost very much uniform in nature. That will ensure that you are not using, for this particular half-toning factor, this will ensure that you are not using very high number of pixels and low number of pixels, and a optimum level is maintained. Now with this knowledge in mind, I am going to introduce this half-toning factor into your optimal scanning resolution formula. Initially what we did, initially it was screening frequency into scaling factor into sampling factor. But now, okay, sampling factor I think I missed out. So yes, yeah. So now the optimal scanning resolution will become screening frequency into scaling factor into sampling factor into halftone factor. So this will become your new formula for considering any scanned image for processing or for correction. Okay. So we have completed one part that is the relationship between the your PPI and LPI. Now we are talking about the next part, that is, which we left out, I think, that was relationship between DPI and LPI. This is another very interesting thing. So here you see, for the same dot to be created, there were 10 by 10, I think 10 by 10 such exposure dots to create a single halftone dot, right? So why this is necessary, that you have to understand first. Let us take a look now. Okay, see, four images of the same thing, but the uh, you know the screen cell, the size of the screen cell, or you can say that the resolution of the, not I will not bring the screen cell here again. Let us only say that the resolution of the CTP that has changed. That means what? The number of exposure dots. Resolution of the CTP means the number of exposure dots. Number of exposure dots that can be given by a certain CTP, that has basically changed. So the same image has been processed, or same image has been reproduced using 4 CTPs. Where in the first case there were how many? 1, 2, 3, 4. 1, 2, 3, 4. So 4 by 4 was the size of the resolution of the CTP. In this case, it was, I think, 1, 2, 3, 4, 5, 6, 7, 7, and here it was, I think, 12. So 12 by 12, and in this case it was 10 by 10. Now, this is exactly what I explained in this particular slide. I drew, no, in this particular slide. You have two CTPs. One CTP is capable of producing 1200 dots in 1 inch, and the other CTP is capable of producing 12,000 dots in 1 inch, right? So this is exactly what is being referred to here also, that if your CTP, you compare this first case and the fourth case, okay? We'll not talk about these two. So don't take a look at here. I'll explain this later on. See, this CTP is capable of producing, let us say, 4 by a screen cell having a resolution of 4 by 4 grid, and this CTP within the same range is capable of producing a screen cell which is having a resolution of 12 by 12 pixels, or 12 by 12 exposure dots, not pixels, exposure dots. That means this CTP is capable of burning areas as small as this small box, but this CTP is capable of burning these big chunks of exposure dots, right, to create this particular dot. As a result of which CTP do you think will be able to create or image at a higher resolution, and which image quality will be better? Of course, this one. So that means what? Greater the image quality, greater will be the, greater the exposure dot resolution, or DPI, a better term, greater will be the image quality, better will be the image quality. Okay, now let us take a look at another thing here. See, in this situation, in this particular case, say this is your input pixel. This input pixel means your digital image. This is the size of your screen cell. So size of your screen cell is, in this case, 8 by 8. 8 by 8 is the size of the screen cell, right? Now just take a look at this picture. One CTP is capable of burning area which is this big. Another CTP is capable of burning area which is this big. Another CTP is capable of burning area, minimum burning area, or minimum exposure area, minimum exposure dot. So better way to say is that one CTP is capable, this CTP is capable of creating exposure dot which is this big. This CTP is capable of creating exposure dot which is this big, and this CTP is able to create dots which is this big for the same area of screen cell. Okay. So which CTP do you think will produce higher resolution images? Of course, this one which is having 12 by 12 screen cell size. Of course, this one. Now, the overall idea over here is that input resolution is what you are getting in your what you are getting from your from your scanner, right? This is the scanner resolution what you are getting. So let us say this is your 120 120 lines per centimeter, right? Or this has been converted into inches, so that is 305 dpi, and your CTP's addressable resolution is 1219 dpi, right? CTP's resolution is 1219 dpi. Okay, now the question is, how or why does this matter, or why I am saying that the image, repeatedly I am saying that the image quality will become better. when your output frequency or your addressable resolution of the CTP increases. See, there is a very easy formula to remember this. I'll just show you. See, the formula is that number of tones that is achievable is equal to addressable resolution by input resolution squared into G minus 1 plus 1. This is the basic formula actually. Okay. So let us explain this formula. What does it mean? See, first of all, number of tones I have to explain. That is the first thing. Number of tone is, suppose this is your grayscale. If you remember our discussion on the concept of bit depth, if you are using a 8-bit or 4-bit image, then what is the number? How many tones will be reproduced for a 4-bit image? It will be 2 to the power 4. That means 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16 tones will be created. So how I will try to show. So this is how the tones will appear, right? 16 distinct tones. But if you are using a 8-bit system, then total number of tones is 256, right? And the appearance of the 256 tone is so, the appearance of that grayscale is so smooth that you are not able, as in case of 16 tones, you are able to distinguish between each of the tone. But if you have a very large number of tone, and that means the difference between one tone from the other is so small that you are not able to detect the difference, and it appears like here it appears to be discontinuous, that is, it is discretized actually, or rendered. But in this 256 or 8-bit grayscale, the difference between one tone and the other is so small that you are not able to basically define or detect the difference between one tone and the other. The entire grayscale appears to be very smooth in appearance, and there is a very smooth gradual change from the shadow to midtone towards the highlight area. So that is what the number of tone here means. Okay, that how many tones can be created by that CTP. Now tell me, before going into the mathematics of it all, can you tell me that if I am using a higher resolution CTP where the resolution of the screen cell itself is quite high, that is, in this case the resolution of screen cell is 12 12 by 12, and in this case it is 6 by 6. So there is pixel per screen cell. Now in this case, why the number of tone will be higher? Can you tell me? See, I will show you, instead of 6 by 6 and 12 by 12, I will show you manually. See here what happens is, let us take two examples. This is 2 by 2, one grid and one screen cell, and this is 4 by 4. Okay, same size of the screen cell size is same, right, in both the cases. What is changed? The resolution of the screen cell has changed. That means the resolution of the CTP has changed, right? This is higher resolution CTP, this is lower resolution CTP. Okay, now total how many tones can be created here? How many tones can be created here? Oh, how many tones I will show you, but just tell me in this manner that suppose I want to create a shadow area or a shadow dot using these 4 pixels here. What can I do? I can switch off all these, or I can burn. I will not say switch off because we are talking about in terms of your DPI and your CTP. I will say that I can burn all this entire thing, right? So shadow, and similarly I can burn all the cells, areas here also, exposure dots here also. I can expose all the exposure dots here, and I can create a complete shadow. Fine. But the problem is, what if, now let me erase this. The problem will be to erase. Okay, we'll try to erase. Okay, so this is fine enough. Now the problem is, if I want to create a certain shade of a particular color or a certain tone, okay, not I will say shade, but I will say I want to create a certain tone. What can I do? I can switch off this particular entire thing, this particular exposure dot. But here in this particular scenario, if I want to create the same tone, then I can do that by simply burning these two cells. That means the size of the dot will become this much. Here the size of the dot will become this much. Now tell me something. You wanted, let us say, you wanted to create 20% dot. Okay. And after creating this particular dot in your CTP on the plate and after printing, you found out this to be, or on the plate this to be as, let us say, 25%, because there will be dot gain and all. So let us say this becomes 25%. Okay. In highlight area this does not happen really. Let us say 22%. Fine. But in this case, your intention was to create a 20% dot, but you do not have any option to create a 20% dot or a smaller size dot, because you are limited by the fact that the minimum dot size that you can create here is this entire thing. So ultimately the resultant dot that will be created in the plate will maybe be 30%, 10% dot, 10% greater, or let us say 12% greater ink will get deposited in this area of during printing onto the paper. That means your intention was to get maybe say a density of 0.5, but ultimately maybe you are getting a density of 0.8 or 0.9. So how much density has increased? So will you get the proper tone? Will you get the proper color value there? No, you will not. So that is why it is very much important to get the proper tones, or it is advantageous for us to ensure that we get larger or greater number of tones, as many number of tones in your plate and ultimately on your paper. This will ensure that you have in your hand a better opportunity to increase the amount of detail in your artwork, in your print, and to reproduce it with as faithfully to the original as possible. Okay, that is why it is important to know why higher range CTP, I mean higher resolution CTP is so needed, in which cases what is the advantage of that higher resolution CTP. But you should also know that there is a catch. I will explain how the maths work. See, for calculating actually, so let me just erase it. So for calculating how much amount of your how many number of tones you can get, or maximum, I should say maximum number of tones that you can get for a certain screen, halftone screen, pair of halftone screen and your CTP, you have this particular formula. What is that? A stands for addressable resolution, maximum addressable resolution you can say of the CTP. I is your input resolution, or input frequency of your in LPI, or you can say in this case you're from, if you're using a scanner then it will come in DPI also. So this is your input frequency, okay, or better let me say LPI only, because we need to establish that relationship between LPI and DPI, that we need to establish. Okay, so let us say that your this thing, oh okay, again G is the number of gray levels. Okay, this is quite interesting. I think I can address this a little bit here. Okay, let me address this here. So gray level is, see, in case of CTP the result is binary. Why binary? Because if this is your, let me show here, if this is your screen cell, let us say 2 by 2 screen cell, then each of the, this is individually is the exposure dot, right? Individually they are all the exposure dot. Now the CTP is capable of burning or exposing with the laser each of the exposure dot, right? Now this exposure is binary. That means this dot will either be exposed, it will be burnt, or it will not be burnt. There is no midway. And you see, that is why you remember in our, I think, first lecture or something, when I was giving you this introduction, I told you that when we get plate files, actually when we generate when we color separate our PDFs to send it to the CTP through the RIP, then RIP actually generates something which is known as the 1-bit TIFF. TIFF is a file format, that's all, but nothing else. But why 1 bit? Now you have a concept of, okay, before going to the mathematics, I have come to this interesting part. Let me explain here itself, and so that you will be having a better understanding at this point. Okay, but the question is, why 1 bit? Now you know what bit depth is, huh? So for a image which is 1 bit size or 1 bit depth image, how many colors are possible? Two colors. Either for digital image, let us say first digital image. For digital image, two colors are possible. That means the pixel is either lighting up, on or off. For your CTP also, I am getting some uh, PDFs, or I am getting some files, not PDFs, I am getting some files which are in format 1 bit. That means it contains areas which the CTP has to burn. So that can have only two outcomes. That file can have two outcomes or two areas which to burn and areas which not to burn, right? So there is burn in the sense, again I am repeating the same thing, burn means laser expose, exposing the area with the help of the laser, exposing the exposure dot with the help of the laser. That is what burning is. So that means the CTP is capable of burning this particular dot, or either it will do one of two things. It will either burn this or it will not. So this 1-bit TIFF file contains information which area the CTP has to burn on the plate. That information is there. That is why it is 1 bit. And TIFF is file format, and this lossless file format. It is supplied to the CTP, and CTP takes it and it burns. Okay, so this is the story of 1-bit TIFF. Okay, now coming back to the concept of gray. Okay, yeah. So I was talking about gray levels. From gray levels, I came to 1-bit TIFF. The concept here is, so for gray level, for 1-bit TIFFs or 1-bit image, how many gray levels are there? In the gray scale, how many gray levels are there? How many colors are possible, or how many tones are there? Let us say for 1-bit image, if I draw a let me draw. If I draw a grayscale for a 1-bit image, how many colors are there? How many tones are there? 2. This one, this is, if we are talking about CTP, then this is burnt and this is not burnt. That means this is image area and this is non-image area. Dot will form here, dot will not form here. That is okay. For offset, we are considering gray level as 2. Either there is image or there is no image. But in digital printing, especially inkjet printing and these things, there are multi-level gray level, multi-scale gray levels. You have some idea about this. Don't be shocked, but you do have some idea about this. In the previous semester, when I talked about proofing, I talked about this dye sublimation technique. This in thermal dye sublimation technique. What is the principle there? How much amount of ink will get deposited on the piece of paper? That determines the tonal gradation. So this becomes shadow, this becomes midtone, this becomes your highlight. So how many gray levels are here? In this particular scenario, for this case, there are 3 gray levels. 3 plus another one, 4. That means another gray level is nothing is there. So total of 4 gray levels are there. Right? In inkjet printing also, there are multiple gray levels. Okay, greater quantities of ink can drop and to give that shadow appearance, lesser quantity can drop to give mid-tone and highlight appearance. So number of gray levels in those digital printing processes is high. Okay, so that is what gray level is. But for our case, we have only 2 gray levels. Either there is image or no image. Okay. So G stands for that number of gray levels. Okay. And 1. Okay. So why this 1? Why this 1? Why 1 is there? 1 is there because this is the case where there is no tone. That means this situation, this situation, this which I wrote later on as +1. No, nothing is there. All the tones plus no tone. That is also a tone. I mean, this is also a tone. That is why it becomes 2. So that is that one tone. Okay. So, for example, um, normally you see our eyes can normally detect differences between 100 tones. Okay. So let us say that we have got a CTP which is having a addressable or output resolution of 1000 dpi, and you are printing an image which is having a input resolution, I mean the halftone resolution that you have chosen for the screen, that is 100 lpi, right? So what will be the number of tone squared? G here for offset, as I told you, is 2. That means 2 minus 1 is 1 plus 1. That means 10 square plus 1, that is 100 plus 1. Okay. Now I am not writing 101 intentionally because let us consider this 100 here is quite important. See, why it was said, if you go back earlier, if you notice that, I don't know, it was said here that DPI should be greater than 10 times the LPI. Why did it say that? 2 times, the PPI is 2 times LPI, that how it happens, that we have established. Okay. Now the question is, why DPI is said to be having greater than or equal to this 10 times LPI? Why is it that? The concept is, basic concept is this. In the next lecture I will go into details of why these 100 tones are important and how it changes when the input resolution changes for different screens, and what impact it has in terms of determining what should be the input frequency for a certain print job, maybe for a certain magazine or a billboard. So all these things in the next lecture, but let us now today we end this lecture by this concept, that is, why 10 times? Why DPI? See, as I told you, our eyes can easily detect difference up to 100 tones. Okay. Anything greater than that, it becomes difficult to detect the difference actually. So it is safely assumed that, or you can say that minimum number of tones, conversely, if I say that minimum number of tones that our eyes can detect to be quite smooth without any distinction between the individual tones, that is 100. That value is 100. That means if I give you a 100 tones grayscale, then you will say, okay, this seems to be continuous to me. Okay, I am not appearing, I am happy with this, even if there is breakage, but I don't mind. This seems to be continuous enough to me. This appearance seems to be continuous enough to me. So that is why getting the number of tones to be 100 is quite important for any CTP, for any printing device for that matter. Okay. Now the question is, how do I get to these 100 tones? Only when this addressable resolution is 10 times the input resolution, that is the halftone screen resolution, only then the resultant will become 100. 100 plus 1, that is 100 will come here, right? That is why it was said that DPI should be equal to, minimum should be equal to 10 times into your LPI, that is your addressable resolution for the CTP should be minimum 10 times of that of the halftone screen resolution that you are using to screen the image with. Okay, so that concept also we come to know. Hopefully this was clear. In the next class we will be talking about details about why these 100 tones are important and how it matters and how it varies and how to determine this halftone screen, which halftone screen to use. I mean, what type of halftone screen, and what should be the value of the halftone screen for a magazine, as I told, and for a billboard, how, why it will be different, and why we can get away with using lower halftone screen for a billboard but not the same we can use with the case of the magazine. So those things we will be talking in the next lecture. Okay, hopefully this was an interesting lecture, hopefully you liked it. All right, so one question I have asked you, that is, I think somewhere I had written down that question for you. Yeah, for this, in this case, the screen cell, what will be the size of the screen cell? Okay, so write down the answer to that in your Google Classroom and see your answers. Okay, thank you for listening.